Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is a second video for students who are taking a Calc 2 class and who are going through work problems or applications of integration to engineering and physics. You should have already watched my video on force and kind of the definition and the concepts of force. Recall, force is mass times acceleration. Generally, we think of that as acceleration due to gravity, but actually it's any type of acceleration. The units, at least in the SI system, are kilogram meters per second squared, and they get the very special name of the Newton. Now, in the previous video, I had mentioned that in the US, which uses the imperial system along with Burma and Liberia, we use the name pounds for our unit of force. Now, technically, there's actually an analog to kilogram meters per second squared in the US system or in the imperial system, but you probably don't know the unit for mass in the US system. Now, the unit for distance that we generally use is going to be feet, and we still use seconds for time scale, so it would still be something times feet per second squared. I'll write that in here. So we have a distance per time unit squared, but we still need to multiply it by the US or the imperial system's version of mass. And oddly enough, the name for mass in the imperial system is the slug. I didn't mention it in the previous video just because it wasn't worthwhile to mention, but it is kind of interesting at least. So there you go. That's what you should know up to this point as far as the work problems go. Now, if you're watching this video, it's likely because your class goes through hydrostatic force and pressure. And to do that, we need to have a discussion about density. In some courses, some Calc 2 courses, you'll approach this topic much later in a Calc 2 course, like almost halfway through the Calc 2 course. However, I tend to do this material at the same time that I do work because it fits beautifully with that material, and it still is applications to physics and engineering. So let's dive into density, because you need to know that before you can start talking about hydrostatic pressure and hydrostatic force. The density of an object is defined to be its mass per unit volume. Now, if you just think about that language, let's forget about the symbols you see down below. And if you just think about the language, and if you think about that we're talking about the SI system or the metric system, then we know mass is kilograms and a volume is just a three-dimensional distance. And distance is in the metric system is going to be measured in meters. So kilograms per meter cubed. That's a mass, one mass per unit or one volume, 1 kilogram per cubic meter. Now, obviously it doesn't have to be a kilogram. We could change the actual mass of whatever we're looking at, but the important part is the units that we have there. And so I'm going to go ahead and continue on with the definition, and we'll write down the formulas in a moment. A common, in fact, the most common notation that we use for density is this right here, rho. This is the Greek letter rho, R-H-O. Rho is going to be the stand-in variable, or I should say the stand-in lettering that we use for density. And often when you speak about density, you're really speaking about fluid, but it doesn't have to be that. It could be solids, it could be gases. Think of it this way, you have some type of liquid. You don't know very much about the liquid, but it's in some vat. And if somebody told you, I have some strange liquid in here, and I happen to know the mass, if you took out a cubic meter of this volume, so a cube of 1 meter by 1 meter by 1 meter, if they told you the mass of that was, let's say, 1,000 kilograms, then the density of that liquid would be 1,000 kilograms for every cubic meter. That is the density. By the way, that's the density of water. Most liquids that we run into have a density between about 500 and 1,500 kilograms per cubic meter, but that is not a hard limit, obviously. Now you can probably see there's a second formula I have right here, and that's if I take the mass per unit volume version of this, and if I multiply both sides by volume, then we just have another formula for the mass of an object. It is the object's density times its volume. That would be the mass of the object. And that actually is a very useful version of mass. So I'm going to write these formulas down. And before I write down the imperial units, because the imperial units are really the oddball units for most situations, it is going to be mass, again, per unit volume. Well, the volume in the imperial system is always going to be in terms of feet, right? So it's feet cubed, or cubic feet is another way of saying that, probably a better way of saying that. And then again, the unit for mass in the imperial system is the slug. Now, something I want to mention here before we move any further, and that just is on the next page, so let me hop over there. As I mentioned, in the metric system, or the System International, the unit for density is kilograms per cubic meter. In the imperial system, it's slugs per cubic foot, but it is incorrectly often cited as pounds per cubic foot, because people think for some reason that pounds is a mass, but that's not true. Pounds is force in the US system. And so technically, if somebody says it's a certain number of pounds per cubic foot, they're actually wrong. Remember, pounds is a unit of force, not a unit of mass in the US system. This won't be super confounding for most students as we move forward. I'm just letting you know that people often engage with the word pounds when they should be using the word slugs. But we'll kind of fix that as we move forward. So now that we have density down, let's start talking about hydrostatic pressure. Because really, when you're talking about density, like I said earlier, you're honestly probably talking mostly about some type of fluid. And then when you start talking about fluids, then you say, well, what if I have some fluid in a container? How much force can that fluid exert upon the edge of that container? And so that's really what hydrostatic pressure is all about. The hydrostatic pressure, which is force per unit area on an object that is d meters below the surface of, and I say the water, but really it's of the fluid. Anyhow, that hydrostatic pressure is given by this formula right here. Now, before I just rattle off the formula, I do want to mention, by definition, hydrostatic pressure is force per unit area. Let me write that down. Pressure is force per unit area. Well, let's go ahead and do this from the metric system side of things. We know force is going to be the Newton. And again, I put the table down here. The units in the SI system for force is the Newton. For right now, we'll keep that there. And then area is going to be in square meters. However, we know the Newton is going to be kilogram meters per second squared. So I'll go ahead and put that in here. So there are a lot of units going on, and actually you can reduce the units a little bit, right? You can clean this up. Meters upstairs will cancel with meters downstairs. You can move the second squared downstairs as well. So you get kilogram over meter second squared. Now that doesn't mean anything to most of us. However, if you decide to multiply both numerator and denominator of this by square meters, which kind of undoes a little bit of the work I just did, but that's okay. If you do that, you get a better interpretation here. We have kilogram meter squared over meter cubed second squared. Well, kilogram per cubic meter, that is actually density. This piece right here. Let me go ahead and show density down here. It's kilograms per cubic meter. So I'm going to go ahead and replace that kilograms per cubic meter with density. And note as well that I split the square meters upstairs into just meters times meters. The reason why I did that is because this right here, meters per second squared, is an acceleration. So I'm going to go ahead and say this is rho times an acceleration times meters. And if you take a look at the formula here, now remember we're talking about a fluid in some type of container. Any acceleration on that fluid is likely only going to be due to gravity itself. So when we write down this A right here, in general, we can assume that the accelerations that that fluid is experiencing is only through gravitational pull. So I'm going to replace that A with acceleration due to gravity. Now, look at the last letter there. The last letter in this formula for hydrostatic pressure is some D. Well, what does D represent? D is how far below the surface of the fluid that little unit area that we're looking at is at. So D is just a certain amount of meters. Well, look at this. The unit we have left over is in meters. So I can go ahead and say that's just a distance, specifically a distance below the surface of the fluid. So this is rho g d. Density, gravitational pull, acceleration due to gravity that is, and distance below the surface of the fluid. G is approximately 9.8 meters per second squared. And the density of water, which is what I originally wrote this definition for, but it actually works for any type of fluid as long as you know the density of the fluid, is 1,000 kilograms per cubic meter. All right, let me go ahead and fill in this information in the table below. Now, the units that we commonly use for hydrostatic pressure, well, it's force per unit area. And like I said earlier, that's newtons per square meter in the metric system. So I'm going to write that down here. And that's known as a Pascal, also noted with a capital P, little a. And again, if we were talking about the US system or the imperial system, force will be in pounds and area will be in square feet. So pounds per square feet. And I'm using the LBS for pounds, just in case you don't know that that's the shorthand for pounds in the US system. So pounds per square feet. And by the way, in the US system, we call that unit of measure a bar. All right, we're getting this table kind of put together nicely. The concept, the related formula, and then the units in both the metric and the US systems. Honestly, when you deal with hydrostatic pressure though, you're dealing with that as part of a bigger problem. So it is a good idea to remember this formula because you're going to use that formula in a bigger style of problem. And it is at this point that a lot of students feel like, oh my gosh, all this physics and engineering stuff in Calc 2 comes along with a lot of formulas. Do I have to memorize all these? And the answer is yes. Generally, you do have to memorize these. Luckily, the formula for force, which is mass times acceleration, is pretty much the one you've always heard about. Density is not too terrible. Just remember it's mass per unit volume. And also remember your algebra that you can multiply both sides by volume to get rid of the fraction there. And the one that's really going to be the one you have to kind of try to figure out how to remember is hydrostatic pressure, which is density times gravitational pull, acceleration due to gravity that is, times the distance that square area of fluid is underneath the surface of the fluid itself. Now, as I've mentioned, the units in the metric system are going to be pascals, right? And in the imperial system, pressure is measured in bars. So both of those things I have already mentioned. This is kind of an oddity here because there's very rare links, like clean links, between the metric system and the imperial system. And this is one of those cases where it's a very clean link between the two systems. The link is that 1 bar in the US system is defined as 100,000 pascals. Another thing to note here, the product rho g, this is going to be an important conversation. This product right here, which is density times acceleration due to gravity, is going to be semi-constant throughout our computations. That is, if you're constantly working in the metric system, and if you're working with water, then the density of water times gravitational pull, well, density of water is 1,000 kilograms per cubic meter, and acceleration due to gravity is roughly 9.8 meters per second squared. Well, that is 9,800 kilograms per meter squared second squared. Don't worry about interpreting the units there. The important part is that when you're working with a constant type of fluid like water in the metric system, you're going to continuously get this constant right here. So like I'm saying, the product, rho g, is going to be semi-constant throughout our computations. It only changes when the liquid in consideration changes. For example, switching from water, which has a density of 1,000 kilograms per cubic meter, to molasses, which has a density of 1,400 kilograms per cubic meter. Well, that obviously is going to change this constant 9,800 significantly because our density for molasses is higher. That's okay. Just once you have the liquid in question and you're constantly dealing with that, then figure out what 9.8 times that is, and you have rho g for the rest of your work. The second note, and this is really important, in the imperial system, which is the US system, we often shorthand that product, which is rho g, as delta. That's a lowercase delta right there. And this is because, remember when I mentioned before that people often incorrectly cite density as, actually, let me bring back my table. There we have it. People often incorrectly cite density in the US system as pounds per cubic foot, and it's not. As I mentioned, it's not pounds per cubic foot, it's slugs per cubic foot. However, if you're multiplying by acceleration due to gravity, you get the following. So let's go ahead and just do that. Let's take density here in the US system times acceleration due to gravity, and let's look at the units. So I'm using the equal sign inappropriately here, but I'm just going to use the units. So we know density is in the US system is slugs per cubic foot. We know acceleration due to gravity is feet per second squared. Now take a look at our unit of force in the imperial system. Right here, it's the pound, but that is actually mass times acceleration, slugs, feet per second squared. Slugs, feet per second squared. That can be traded out for the word pounds. And so it turns out that, yeah, density is not in the US system pounds per cubic foot, but density times gravitational pull is pounds per cubic foot. And that is what you're going to be working with when you work in the US system. You're just going to glue together density and gravitational pull, and you'll get pounds per cubic foot. And if, by the way, that is water that you're working with, it's roughly 62.5 pounds per cubic foot. This is only for water. I should make that note here. If we change the fluid to something more dense like molasses, then that 62 is going to change as well, because the density of molasses is 1,400 kilograms per cubic meter, and we'd have to find the corresponding density in slugs per cubic foot. Anyhow, so as you move forward, you don't know it now, but as you move forward, a lot of your formulas are going to involve rho, g, and something else. My advice to you is when somebody tells you, oh, the density, if you're working in the US system, they're going to say, oh, the density of this fluid is so many pounds per cubic foot. Really what they mean is the density times the pull of gravitation. So in your formula, you're going to glue those two things together and rewrite them as just a delta. And you're going to consider that a fake or a pseudo density in the US system. You'll see this as I go through examples in future videos, but just to let you know, that is often a tripping point that you can get past if you just realize that people, when they say density in the US system, they are really meaning density times gravitational pull. Finally, we get to hydrostatic force. So remember, hydrostatic pressure was force per unit area. Well, hydrostatic force is defined as follows. If a constant pressure P is acting on a surface with area A, so we're back to pressure and area, then the hydrostatic force on the surface is defined to be F equals PA. Force is equal to pressure times area. Now, to be honest with you, we already knew this. You might not notice it, but we did actually run into this already. Remember, we already had said pressure is force per unit area. So what does that mean about the hydrostatic force? Well, multiply both sides by area and you get pressure times area is equal to force. So all we did was take our formula for hydrostatic pressure and kind of rewrite it. But I'm still going to write a line down here for that. And before I actually finish this out, the formula for force, hydrostatic force, is pressure times area. But we happen to know the pressure is rho GD, right? Density times acceleration due to gravity times the depth below the surface of the fluid, of the slice of water that you're looking at, times, again, we need the area, so times area. Now, if you think about the units here, the units of hydrostatic force are going to be the Newton, first of all, because that's just the unit of force in the metric system, and they're going to be pounds in the imperial system because, again, that's the unit of force, so that should work out. Remember, density in the metric system is kilograms per cubic meter. You have acceleration due to gravity, which is meters per second squared. You have a depth, which is in meters, and you have an area, which is in square meters, and the square meters times the meters becomes a cubic meters, which cancels with the cubic meters downstairs, and you will end up having kilogram meters per second squared, which is the Newton. So anyhow, you don't need to actually do all the mechanics here. I'm just going to go ahead and erase this and just say it's the Newton, and here is the pounds. Or singular, the pound, I suppose, is probably the more appropriate way of saying that. Now, again, the purpose of this video was to build up all the language you'll need to then start delving into problems or higher level thought processes in your classroom. So when you approach your class with all this knowledge in hand, maybe on literally in hand, maybe on a little note card so that you remember what all these objects are and what their units are, then you can just delve into using them within problems. A lot of the stuff becomes more clear as you use them within problems, by the way. So don't feel as though you should suddenly have some innate knowledge of hydrostatic force and pressure and density and force from this video. That is not the point. The point is just to introduce you to the language so that in the future you can use that language in problems and conversations in the classroom. Anyhow, I hope that this was not too daunting, and I hope to see you in future videos. Have a great day and be a great human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.